Hello and welcome to the next lecture. The profiler in R is a really handy tool for when you are developing large programs or doing really big data analysis and you are essentially running R code that's taking a lot of time or longer than you want to wait. And of course that's all relative and depends on what you are working on, and maybe there are some other things that you can do while you are running a program. But if something's taking a long time, then profiler is a really handy tool to figure out exactly why it's taking so much time and to suggest kind of strategies for fixing your problem. So I'm going to talk a little bit about using the R profiler and kind of talk about when you might need to use it. There are also some other tools that I will talk about that will help you time your programs, time your functions, and so the conjunction of the profile with these other tools is a really handy toolbox for figuring out how to optimize your software. So let's explore it more. The first question you want to ask yourself is your code actually running slowly? And sometimes you can solve this problem by just running your program and then doing something else, but sometimes that's not an option and you need your program to really run quickly. And so profiling is a systematic way to examine how much time is being spent in various parts of your program, and it's particularly useful when you are trying to optimize your code. You're trying to squeeze a lot of efficiency out of some code, and a lot of times when you first start writing code, it runs fine when you are running it once, and maybe you are running a small piece of a function or a small piece of a larger program, and it looks great when you are running it. It seems to run very quickly when you are doing it, but then sometimes these pieces get embedded in a much larger program. It may be that a larger program is running your piece 1,000 times or 5,000 times or even 10,000 times, and then your one little piece which was running great when you were running it is kind of slowing down everything else because it's being run 10,000 times, and so now you need to make it a lot faster because it's being iterated over a lot. And so profiling can come into play when, for example, if you have a piece of code that runs great, but then when it gets embedded in a larger piece, its speed becomes much more noticeable. So in general, when it comes to optimizing your code, the general rule is that you shouldn't do it. And what I mean by that is that you shouldn't think about it at first. The first thing that you should think about is kind of how to get the code to run, how to make it readable, how to make sure that other people can understand what you are doing. And one of the reasons is that it's often difficult to understand where exactly your program is spending all of its time. And in order for you to speed up your program, you need to be able to know where it's spending its time. And so this cannot be done. It's difficult to do this, well, I should say, without a formal performance analysis or profiling. And so the basic idea is you should always design your code first and make it in a way so it's understandable, and then after you have got something working, then try to optimize it. And then the famous phrase is premature optimization is the root of all evil. If you try to optimize first, the chances are that you will introduce bugs before you even get a chance to kind of get things working in the first place. Once you have decided that you want to optimize your code, then you should act like a scientist. Just like you would in any other context, you should collect some data. Alright, so if you have a sense of where your program is kind of being bogged down or where it's spending all its time, you should collect the data to figure it out. And the way you collect the data is by profiling. So the first tool I'm going to talk about is actually not the profiler. It's a very simple function called system.time in R. And what system.time does is it takes an arbitrary R expression and evaluates that expression and then tells you the amount of time it took to evaluate that expression. Now this expression could be a very simple like a single function call, or it could be very complicated and wrapped in curly braces. So it could actually be a very long expression if you want it to be. The basic idea is that you take this expression and it gives you the time in seconds that was needed to execute this expression. If there's an error in the code while the expressions are being evaluated, then you will get the time until the error occurred. Now there's two very important notions of time. When you are executing expression on the computer, the first is called the user time, and this is the amount of time that's charged to the CPU or CPUs for running this expression. Okay, so roughly speaking, this is the kind of time the computer experiences. The elapsed time is sometimes called the wall clock time, and this is the amount of time that you experience. Alright, So even though you are the user, you are not the user time. You experience the elapsed time. And so the two different notions of time can have different importance depending on what you care about the most. So usually the user time and the elapsed time are relatively close because the amount of time that the computer spends to do executing your function or expression is roughly equal to the amount of time you spend waiting for it, right? These are for standard kind of computing types of tasks. However, there are times when the elapsed time will be greater than the user time, and there will be times when the elapsed time is smaller than the user time. So the elapsed time can be greater than the user time. So that means you spend kind of more time waiting around than the computer actually spend dealing with your code. And the reason that the computer may spend a lot of time reading around for other things to happen that are maybe external to the program itself. And so the CPU doesn't actually spend a lot of time working on your code. It may be spending a lot of time on other things that are going on in the background. If the elapsed time is smaller than the user time, this most commonly occurs if your machine has multiple cores or processor and is capable of exploiting them. So most of the computers these days have at least 4 cores or multi-core machines, and so this is a very common situation. However, it's not always the program that you are running will be all to kind of exploit the use of multi-cores. In particular, the basic R program does not use multiple cores as of yet. However, it often links to libraries that do use multiple cores, and the most common one would be the linear algebra type of library. So if you are doing something like regression or a lot of these prediction routines or matrix computations, these all involve linear algebra libraries, and many of these libraries have been optimized to use multiple cores, and so they are called multi-threaded BLAS libraries for the basic linear algebra standard libraries or subroutine libraries. And on the Mac, sometimes called veclib or accelerate, there are more general libraries like Atlas for AMD machines, there's ACML, and for Intel machines there's MKL. There's also parallel processing libraries, for example the parallel package, which can use multiple cores, but it can also use multiple computers. And so this will potentially lead to a program that takes more user time than it does elapsed time, and I will give an example of how this works in a bit. So one example when elapsed time will be bigger than the user time is if you read something from the web. So here I'm just using the readLines function to read a web page of a remote server, and you can see the elapsed time is about 0.4 seconds, but the user time is about 0.004 seconds. So the CPU actually doesn't spend a lot of time running this code because the chunk of the time is just spent waiting for the network or waiting for the data to kind of go over the network and to come back to your computer. And so waiting for the network to kind of deal with the data going there and coming back is not really part of your program. It's part of a different thing that the computer is doing. And so the amount of time executing your program, in this case just the readLines function, is relatively small. And the second example, this is where the elapsed time is less than the user time. I have created a simple function which creates a Hilbert type matrix, and I calculate the singular value decomposition of this matrix with the SVD. So the SVD function makes use of the accelerate framework on the Mac, which is a multi-threaded linear algebra library, and so it can take advantage of the two different cores of this computer that I am using. And so you can see that the user time was roughly almost double of the elapsed time. So the elapsed time was about 0.7 seconds and the user time was about 1.6 seconds. And the reason is because the underlying linear algebra library split the computation across the two cores, and so you can think of it as the elapsed time was multiplied times 2 because it was being executed on two different CPUs. So the amount of time that the CPU spent working on your program was actually more than the amount of time that you spent waiting for it to come back. You can also time longer expressions by just wrapping everything in a set of curly braces. So here I've got a for loop that's just generating some random normal variables, and you can wrap that whole thing in curly braces and call system.time around it. And you can see that here this is a very simple expression. It's not multi-threaded, there's no network activity, and so the user's time and the elapsed time are basically the same. So this is sometimes a really handy function if you just want to take a little bit piece of code, figure out how long it takes to run it, and may kind of go through a program expression by expression or line by line to see which parts are taking a lot of time. Now the part of problem with system time is that it assumes that you know where the problem is and that you can call system time on a given expression, and so this may be useful for smaller programs, for less complicated programs where you have a very good sense of kind of where the bottlenecks are. But the question is, what if you don't know where to start? What if you don't know where the problems might be and where to start looking? And so you need another function to kind of help you along with that. And so that's Rprofiler, and the Rprofiler has a function in R that's called Rprof, and it is used to start the profiler in R. One could note that R must be compiled with profiler support, and so it's not something that's going to build in all the cases. However, I'd say 99.9% of the cases this is the true. R will only be compiled without profiler support in some very special circumstances. The other function that's useful is the summary.Rprof function, which takes the output from the profiler and summarizes it in a way that's kind of readable, because the raw output from the profiler is generally not very usable, and so the summary.Rprof function is very important. It's important to know that you should not use the system time function and the Rprofiler function together. These are not really designed to be worked together or to be used together. So you should always use one or the other and not both. So the Rprof function, basically what it does is it keeps tracks of the function called stack at regularly sampled intervals, right? And so basically as your function is running, it kind of queries the function called stack. So how many functions call other functions, and it just prints it out. Basically all it does is it prints out the function called stack at very quick intervals. Default is every 0.02 seconds, and it prints out the function called stack. So first thing you will notice is that if your function takes less than 0.02 seconds to run, then the Rprofiler will be useless, and in general because it will never sample the function called stack. And if your program runs very quickly, the profiler is not useful. Well, of course, if your program runs very quickly, you probably wouldn't think to run the profiler in the first place. So it's usually not a problem, but you really need to use the profiler in situations where your code is taking much longer on the order, at least on the order of the seconds. So here's just a quick example of the raw output that comes from the profiler. Now generally speaking, you will not ever use this output, but I thought it might be interesting to look at what's going on. So you can see that I'm just calling the lm function, which is kind of a univariate outcome to a univariate predictor. And what happens here, as you can see that each line of this output is the function called stack. So you can see at the very right is kind of the top, and at the very left is kind of the bottom, so to speak. And so the very right, you can see that lm was called, and lm called eval, and eval called eval. So I'm going from right to left here, and eval called model frame, which called model frame default, which called eval again, and eval and the list. So all these functions call each other. So you can see that the function callback goes out for a deep. As you go further in the evaluation, you can see that the function calls that changes. So at the very bottom, you can see that lm called lm.fit. And if you are not familiar with the lm function, lm.fit is really the workhorse of this function. It does all the kind of computation, and so you wouldn't suspect that it would spend a reasonable amount of time in the lm.fit function. As that kind of raw output is not particularly easy to read, so we use the summary.Rprof function to tabulate the Rprof or the output and calculate how much time is spent in which function. So the idea is that once you see that the function called stack, you know that each line of the function called stack is separated out by 0.02 seconds, and assess the frequency which is sampled. So given that you can calculate how many seconds are spent in each of the function, because if it appears in the function called stack, then you must be spending some time in it. So there are two methods for normalizing the data that you get from the Rprofiler. One is called by.total, which divides the time spent in each function by the total runtime, and by.self, which does the same thing, but first subtracts out time spent in functions above in the call stack. So it's important to realize that the two separate concepts here are by.total and by.self. The basic idea is that by.total, I mean normalizing by the total amount of time spent in a function, gives you basically how much time was spent, that how many times that function appeared in the calls in the kind of printout. And so for example, 100% of your time is spent in the top level function, right? So the function that you call, suppose it's lm, you spend 100% of your time in that function. Basically it was at the top level. And so, but the reality is that often the top level function don't really do anything. That's kind of important. All they do is they call helper functions that do the real work, right? So chances are if your function is spending a lot of time doing something, it's spending a lot of time in those helper functions, which is just being called by this top function to kind of do all the work. And so often it's not very interesting to know how much of time is spent in these top level functions, because that's not where the real work occurs. Alright, so you really want to know kind of how much time is spent in the top level function by subtracting out all the low level functions that it calls, right? So it turns out that it spends a lot of time in the top level function, but even after you subtract out all of the lower level functions, then that has something that's interesting. But most of the time you will notice that when you subtract out all the lower level functions that get called, there's very little time that spends in the top level function. And because all the work and all the kind of computations is being done at the lower level function. So that's kind of where you want to focus your efforts. So the by.self format I think is the most interesting format to use, because it tells you how much time is being spent in a given function, but after subtracting out all of the other time spent in lower level functions that it calls. So it gives you, I think, a more accurate picture of, which functions are truly taking up the most amount of time and which functions that you might want to target for optimization later on. So here's an example of some output in the by.total format, and you can see very clearly at the very top that 100% of the time is spent in the lm function. So the total time was 7.41 seconds for this run, and all of it was spent in lm. Of course, because lm was the top level function, but you can see that the second place winner was the lm.fit function. As I mentioned before, lm.fit is where a lot of computation occurs, and so that was 3.5 seconds, and so about half of the time in that function. Now you also see that a number of functions here, model.frame, model.frame.default, eval, all these functions don't really involve computation, but there is a reasonable amount of time spent within those functions, so that's kind of interesting. Now I think the more useful output is the by.self output, which kind of subtracts out any lower level function calls, and calculates the amount of time truly spent in a given function. And here you can see that lm.fit is the clear winner, because that's really where all the computation occurs. In particular, lm.fit calls a fortran routine for inverting a matrix, and so that's usually where in most large scale regression problems, that's where all the computation occurs. The next function that takes a lot of time, apparently, or 11% of the time, is the as.list function. For the as.list.data.frame method, it's not immediately clear why so much time is being spent in this, but it's maybe something you want to investigate, because it may be something that's not very important to the kind of core computation, and so you can kind of go down the list here and see how much time is being spent in various functions. And then you will see a lot of these functions don't directly pertain to computation or kind of core computation, but they are really more kind of pertain to data, formatting of the data and things like that. The last part of the summary.Rprof output is just the sample interval. So you can see what time interval the sampling took place for printing out the function called stack. So you can see it's 0.02 seconds. And the sampling time, which is just the total amount of time that the expression took to run, this is the same, I think equivalent to the kind of elapsed time in the system.time function. So that's a quick tour of the R profiler in R. It's a very handy tool for doing performance analysis on R code to give you some useful feedback, and I find often highlight functions that you may not have suspected as being kind of time hogs or bottlenecks, and because they are not really core to the kind of real computation that you are working on, so the profiler can be really useful, I think, for highlighting these kind of situations and often finding things that you kind of unexpected. The summary.Rprof function summarizes the output from Rprof and gives you the % time spent in each function. And I think the by.self normalization is the most useful for kind of highlighting bottlenecks in your code. One of the implications of using the profiler is that it's useful to break your code into functions. So rather than have one massive function, it's useful to break your code into kind of logical pieces of different functions. and so the profiler can use this information to tell you where the time is being spent. So remember, the profiler prints out the function called stack, and if you break your code into multiple little functions, the function names that you give will kind of serve as little identifiers in the function called stack to tell you kind of where the code is spending the most amount of time. So that's another little strategy that can be useful when you are profiling your R code. The last thing that's worth learning is that if your R code or any other R code called C or Fortran code, this C and Fortran code is like a black box. It's not profiled and you won't see any information about that code. All you will know is that some time is spent there, but you won't know any details about that. So overall, I think the profiler is very useful. I encourage you to use it rather than just try to guess at where to optimize your code. And the profiler can be used to kind of collect data about where time is being spent. So that was all for today. I hope that you will find this lecture very useful going further in R programming for data science problems. And if you liked this lecture, then don't forget to hit the like button, sharing it with your peers, classmates and friends so they could learn it too. And finally, subscribing our channel so you don't miss the future lessons. So see you in the next lecture.